In this video, I will explain the important formulae from the Laplace transform. Up to now, we have discussed the Laplace transform of the different signals. Now, I want to write all the signals Laplace transform equations here, right? So, first of all, I am taking constant. Laplace transform of 1 is 1 by s, and similarly Laplace transform of k constant is k is constant here, k by s. Then Laplace transform of e to the power of minus at. See, all these equations directly I am writing unilateral Laplace transform, right? And if you want to write bilateral Laplace transform of all these functions in time domain, the given functions multiplies with u of t, right? So, Laplace transform of e to the power of minus at is 1 by s plus a. Laplace transform of e to the power of plus at is 1 by s minus a, which gives the opposite symbol here. And later I am writing one more equation here, Laplace transform of t into t here. So that is 1 by s square, and Laplace transform of t to the power of n is n factorial by s to the power of n plus 1. And now I want to multiply these functions here. So Laplace transform of t into e to the power of minus at. Laplace transform of t into e to the power of minus at is 1 by s plus a whole square. And one more equation also there. Laplace transform of t to the power of n into e to the power of minus at is, so n factorial by s plus a whole to the power of n plus 1, right? And again I want to write a sinusoidal functions equation. So Laplace transform of sin bt. Laplace transform of sin bt explains the b by s square plus b square, and Laplace transform of cos bt. Cos bt is s by s square plus b square. See, all these basic equations are important because to find the Laplace transform of any function or given time domain signals, so we have to use all these equations, and these are used to find the inverse Laplace transform also, right? So similarly here I am writing now the Laplace transform, the sine function multiplies with exponential function, so e to the power of minus at into sine of bt, e to the power of minus at into sine of bt. Then s is replaces by s plus a, so s plus a whole square plus b square, right? One more equation, Laplace transform of e to the power of minus at into cos of bt, cos of bt. This explains the s plus a by s plus a whole square plus b square, right? And now we have to take this complete sinusoidal functions multiplies with exponential signals, but that exponentially increased function e to the power of plus at. Laplace transform of e to the power of plus at into sin bt, then which becomes directly b by, sine function is there, right? So b by, here plus at is there, so it becomes now s minus a whole square plus b square, right? And Laplace transform of e to the power of plus at into cos of bt, so cos bt function is s by s square plus b square is there, and in that function s is replaces by s minus a here, so s minus a by s minus a whole square plus b square. And similarly we have tried the Laplace transform of hyperbolic functions. So hyperbolic functions like this, Laplace transform of sin h bt, so Laplace transform of sin h bt here, so h explains the hyperbolic functions. Laplace transform of sin bt is b by s square plus b square. If it is a hyperbolic function, then you have to write the denominator part, it becomes minus, the sign of the denominator changes because hyperbolic function means imaginary parts are not considered here, items are not used. So Laplace transform of cos h bt is, here we have to write s by s square minus b square. So All these are comes under standard equations, right? And again we have to multiply the sinusoidal functions with t also. So Laplace transform of t into sin bt. Sin bt. See, sin bt function is Laplace transform of sin bt is b by a square plus b square. And whenever t multiplies in time domain, in frequency domain, it performs the differentiation operation. So directly I am writing now like this: minus d by ds of the given function is b by a square plus b square. Right? So whenever t multiplies in time domain, in frequency domain, it performs differentiation operation. Otherwise, we can take directly the denominator power is increases. See, here e to the power of minus at is 1 by s plus a. If t multiplies with this one, e to the power of minus at into t, 1 by s plus a, denominator power is increases. Sometimes some constant multiplies in time domain, some constant multiplies in numerator part, right? So from that, if you simplify this directly, which gives it 2bs by a square plus b square. Now directly I am writing one more equation: Laplace transform of t into cos bt. It's like this: a square minus b square by a square plus b square whole square. Right? Denominator power is increases. Here also it is increases. Power increases. 2bs by a square plus b square whole square, and a square minus b square by a square plus b square whole square. So whenever t multiplies in time domain, denominator power is increases, and in numerator some constant multiplies. That is depends on the given function. Otherwise, remember this property: Laplace transform of f of t is f of s. Laplace transform of f of t is f of s. If t multiplies in time domain, t into f of t is f of s differentiation. So minus d by ds of f of s, right? So differentiation in frequency domain. Otherwise, one more equation also we can write like this: Laplace transform of t to the power of n into f of t. N times t multiplies here. So then it becomes like this: minus 1 whole to the power of n into differentiation here n times. Differentiation n times with respect to s. So these are the standard statements. From this property, I have wrote these two equations. So all these are comes under basic important formulae from the Laplace transform topic, right? So please take this now.